In the last video, we talked about definite integrals. That was finding the area under a curve from one value to the other. Today, or in this video, this part of this lesson today, we'll be talking about indefinite integrals. And eventually we'll get to the point where we talk about how these two things work together. So let's talk about indefinite integrals. But before we do that, actually, let's just do a refresher on the mechanics of the power rule. And I'll explain why in just a second. So we're going to differentiate. We're going to differentiate y equals negative 3x cubed. And specifically, I want you to find dy. Okay, so we're going to find the derivative of this, and we're going to do this in a very, very thoughtful, formal way, because I want you to think about how to work backwards from this process. So with the power rule, what we know is that you multiply the exponent by the coefficient. That's the first step we take. Coefficient. Okay, the next thing we know to do then is to subtract 1 from the exponent. This is something you know now. You've done this a lot. You don't even have to think about it anymore. But it's going to be important to think about these steps so that we can do our next idea. But let's get there in a second. So let's find this derivative. Derivative of y dy over dx, dy dx. Derivative of negative 3x cubed. So I multiply 3 times negative 3, that's negative 9. And then I subtract 1 from that exponent, so that's x squared. And then finally, to find dy, I'm going to isolate that dy. I'll move the dx over to the other side, like so. This is what's called a differential. This is dy, this is the change in y as x is changing. Okay, the reason I wanted to walk through that is because now what we're going to do is find the indefinite integral. Another way to think about this, or another way we say it, is find the antiderivative. So it would look like this. It would say evaluate, actually what it would say is find the antiderivative of negative 9x squared dx. That's what it's saying. That's what it would look like. What this means is that we know that dy is negative 9x squared dx. We know that that's what that is. What we're trying to find is what was the y, what was the original equation that gave us this as a derivative. So this is what's called the antiderivative. Work backwards from the derivative and find the original function. Now it's interesting because it's the same symbol that we were using for the area under a curve. It's still this integral. And this indefinite integral and a definite integral, or the area under a curve, definitely have a relationship. But before we get to that, I want to make sure the mechanics make sense to you so that when we tie this relationship together, you won't have to worry about the mechanics as much. Okay, so what we're saying is find the original function. So we're saying that y is going to equal negative 9x squared. Oops, I don't know why I did that. Negative 9x squared dx. Sorry about all of the button pushing. I'm not sure my hands are getting in the way. All right, what we're going to do then is find y. We're going to start, though, with the original equation we had, dy, negative 9x squared dx. And formally what's happening is we're undoing everything that we did above. So if you look at the last thing we did above was we moved the dx over with the negative 9x squared. So in this case, if we bring the dx back over again, we have dy dx equals negative 9x squared. If I work backward from both of these, so if I say what was the antiderivative, what was the original function that gave this to me, I know that the antiderivative, or the original function that gave me dy over dx as a derivative, is y. The antiderivative of dy dx is y, because the derivative of y is dy dx, doing and undoing. All right, now let's look at this 9x squared. Let's work backward from the power rule. We know this is a power rule because this is just a polynomial. So if we work backward from the power rule, the first step we have to do, because remember the last step we did in the power rule was to subtract 1, so our first step in working backward is to add 1 to the exponent. All right, if I add 1 to x squared, now I have x cubed, okay? The first step in the power rule was to multiply the exponent by the coefficient. So now in our effort to work backward, we're going to divide the coefficient by the exponent. Okay, so if I take negative 9, divided by the new exponent, which is 3, I end up with exactly what we started with up above, which was negative 3x cubed. Okay, we have an issue. For those of you that have taken Calculus AB, hopefully you're remembering what the issue is here. Let's look at this issue. I'm going to change colors for this one because it's pretty important. So let's look at, I would like you to differentiate. And in this case, I would like you to find dy for each of these following problems. So we have y equals negative 3x cubed, y equals negative 3x cubed plus 5, y equals negative 3x cubed minus 1,000. Please find dy for each of those. And I want you to tell me what you think the issue is with what we did up above. Pause the video, go do it. Okay, welcome back. So let's find the derivative, let's find dy for each of these. We already did the first one up above. Dy is negative 9x squared dx. If I look at this second one, I'm going to find dy. Negative 3x cubed, the derivative of that is negative 9x squared. And the derivative of plus 5 is 0. So then negative 9x squared dx, dy equals negative 9x squared. The derivative of negative 1,000 is 0. So what I notice, what the issue is these all have the same derivative. So if I asked you, what is the antiderivative of negative 9x squared dx, which one would it be? Would it be this when we find the antiderivative? Would we add a 5 to the end? Would we not add anything at all? What we need to do in a situation like this, actually in any derivative, we need to account for the fact that there could have been a constant at the end of the derivative that, or the original function that we differentiated. Let me show you what I mean. So if we find the antiderivative of negative 9x squared dx, we know that for sure the polynomial part of this was negative 3x cubed. But there also could have been some constant tagging along on the end. So for any antiderivative you take, for any indefinite integral, we need to add that plus c. We need to account for the fact that the original function could have had a constant at the end of it. So really, if I were to solve negative 9x squared dx, there are so many different solutions to this problem. Graphically speaking, it would look like this. Graphically speaking, negative 3x cubed could have been, it's a little bit steeper, could have been this one. So c could have been, well, 1/2 since I missed the origin. Or c could have been 3, or c could have been -5. So there are multiple solutions to this antiderivative problem, depending upon what that c value is. Okay, let's try another one. Let's just practice finding an antiderivative. I'll do one more with you, and then I'm going to give you a couple to try on your own, and then I'm going to show you one more thing, and that'll be it for this section. So I'd like you to think about what would be, I would like you to integrate each of these things. In other words, I want you to work backwards to find what was the original function that gave me this antiderivative. So let's see, let's do one that's not too crazy hard. 4x squared plus 5x. I'm going to do this one with you because I want to talk a little bit less and just do a little bit more. I will only do this next step one more time. I'll only do it on this one. I just want to show you what's happening with that dx. So really what we're saying is that the derivative was 4x squared plus 5x dx. So dy over dx was 4x squared plus 5x. What we're doing then is we're trying to work backward from this. We know working backward from dy dx, that's y. Working backward from 4x squared plus 5x, we're going to take each one and work backward from the power rule. So in 4x squared, I'm going to add 1 to the exponent, so that's x cubed. Then I'm going to take the coefficient, that's 4, divide by this new exponent, so 4/3. Okay, I'm going to do the same thing for 5x. That's x to the first right now, so if I add 1 to that exponent, that's x squared. And then if I take the coefficient, divide by that x, or divided by that squared, divided by the exponent is 5/2. And we have to think about the fact that there could have been a constant in the original function because the derivative of that constant was 0, so it wouldn't have shown up in the derivative, so we need to take that into account. From now on, when I solve these problems, and you should do the same, I'm not going to write these two steps. We can omit this because it's really formality, but I just wanted to show you what's happening to that dx, because that question comes up a lot. Well, what happens to the dx when we find the antiderivative? Well, that's what happens to the dx. We move it back over with the dy, we know the antiderivative of dy dx is y, so on and so forth. So when I see a problem like this, I'm going to just know that this dx came from the dy, and I'm really just going to find the antiderivative of 4x squared plus 5x. So this would be 4/3 x cubed plus 5/2 x squared plus c. No need to write anything else. All right, I'm going to give you a couple to try. I would like you to try this one. And this one. And one more. I would like you to try this one. This last one's going to be difficult. So take a moment, see if you can find each of those antiderivatives. Go do it, and then come back. Okay, hopefully you gave it a try. This first one, there is no x there. So what I'm going to think about here is we've got 6, and if I really think about it, this is 6x to the 0 power, if you really want to think about it, because x to the 0 power is 1. If I work backward from this using the power rule, I would add 1 to that exponent, x to the first, and then I would divide 6 by that exponent. 6 divided by 1 is 6x. Don't forget about the fact that there could have been a constant, so it's 6x plus c. Okay, let's look at 3 now. The derivative was 0. We can try what we did up above. We can write this as 0x to the 0. If I add 1 to the exponent, that's x to the first, And then 0 divided by 1 is still 0. But 0 is not the only thing that we can differentiate and get 0 for a solution. This one's a little bit tricky. So we got the value of 0 for a derivative. The only thing that gives us a value of 0 when we differentiate is a constant. So the derivative of 0 is just some constant c. That's a weird one. That's a weird one, because the derivative of any constant is 0. The nice part is you can always check your answers by differentiating again. So if you find the derivative of of your answer and you get what you started with, then you know you've done it right. So the derivative of a constant is 0. We had 0 as the integrand. All right, number 4 is tricky. We don't know how to find the derivative of antiderivative of a quotient rule. But what we can do is work backward from the power rule. So we're going to rewrite this first. First thing first, I'm going to rewrite this as x to the 1/2 in the denominator. Okay, but it's still a quotient. That doesn't help us much yet. What I'm going to do next then is bring that x to the 1/2 up to the top. So now it's x to the negative 1/2. But that still doesn't feel right, because now that's the antiderivative of a product, and we don't know how to do that yet. So let's do one more step. If we just distribute that x to the negative 1/2 in. So remember, we add the exponents. X to the first times x to the negative 1/2 is x to the positive 1/2. And then 1 times x to the negative 1/2. Now we don't have a product, we don't have a quotient. This just looks like the power rule. So we'll work backwards from the power rule to find this antiderivative. I'm going to add 1 to 1/2. So this exponent is now 3/2. And I'm going to take the coefficient, which was 1, and divide it by 3/2. Of course, I'm not going to leave it that way, but I just want to show you what I'm doing. Okay, the next step, I'm going to add 1 to that negative 1/2 exponent, so that'll make this positive 1/2. The coefficient is 1, so I'm going to do 1 divided by 1/2. And then don't forget to add a constant. All right, we're going to simplify this. 1 divided by 3/2 is just like saying 1 times 2/3. So this is 2/3 x to the 3/2. 1 divided by 1/2 is like 1 times 2/1. So this is 2x to the 1/2 plus a constant. You can always find the derivative of that to make sure you did it right. Okay, let's go now to one more idea. What we've been finding is what's called the general solution. So we found the general solution to a differential equation. The differential equation in our last case was this, x plus 1 square root over the square root of x times dx. And the general solution we found is we're saying, well, it could be any one of an infinite number of polynomials that has this structure with some general solution, general value for c. So that's the general solution, is what we've been looking at. We don't know the value of c. Now we're going to find the particular solution. Time for a different color. Okay, now we're going to look for the particular solution. So we're going to find the particular solution to the differential equation with the initial condition. That's a mouthful. That's a lot. But we'll get there. So I'm going to give you an example. I'm going to, let's see, f prime of x is 6x minus 8x cubed. And the initial condition is that f of 2 is equal to 3. So what this is saying is, find the antiderivative and then find the particular value of c that will fit this criteria. This is the initial condition. This is the differential equation. It's a derivative. All right, so what we're looking for is what is f of x? And specifically at this point, or that goes through this point, f of 2 equals 3. All right, let's integrate this. We're going to find the antiderivative of this differential equation of 6x minus 8x cubed. All right, we're going to work backward from the power rule. So I'm going to add 1 to the exponent, that's x squared. 6 divided by 2 is 3. Add 1 to the exponent, so that's x to the 4th. 8 divided by 4 is 2. Plus we have some c value. So we just found f of x. We just found the general solution. What we need to do now is use the information that was given to find the particular value of c so that this function will go through the point 2, 3. All right, so the initial condition means that this condition is the point 2, 3. That means that this function must go through that point, so what value of c would make that happen? Well, we know the y value then is 3. We know the x value is 2. And we can use that to find c. Order of operations, 2 squared is 4. 4 times 3 is 12. 2 to the 4th, 2, 4, 8, 16. 16 times 2, that's 32. 12 minus 32 is negative 20. And if I add 20 to the other side, I get c is equal to 23. So we're not done yet. We found c, but we haven't found the particular solution. So the final answer to this is that the particular solution for all of the information that's given to us is this. That is your solution to the problem. Okay, that's a lot, but we did it. Now it's time for you to go practice.